Alright, now that we have enemy navigation in place, let's take a look at putting our first state-based behavior in place inside of our game demo. In this video, we are going to establish enemy player seeking. So we're going to put together the check necessary for the enemy to see the player when the player enters the enemy's sight radius, and at that point change the enemy's state so that he begins chasing the player instead of wandering around the level. To get started, we're going to be coding here inside of the scene game class, and we are going to begin inside of the update method. The first thing we need to do is we need to establish that point in time when the enemy sees the player. The way we'll do this is actually with a distance-based, you could say, collision check. We're going to see if the player has collided with the enemy's sight radius rather than the enemy itself. So we'll put this together as an if statement inside of update, and in order to see if the player has entered the enemy's sight radius, we will do a distance check. So we'll say if vector2.distance between the player and the enemy, so that's player.position and enemy.position. So we'll say that if this distance is less than the radii of the player and the enemy sight radius, then that means the distance is actually within the radius of each. So we'll say that if this distance is less than player.radius plus enemy.sight radius. So again, if the distance falls where these two are overlapping, where the player radius and the enemy sight radius overlap, then the player has just entered the enemy's sight radius. So at this point, the enemy needs to change its state from wandering to seeking the player. So we'll do this by calling our enemy, and we will invoke its change state method, and we will change our state to enemy state.seek player. Alright, with this in place now, we've changed our state, but right now nothing is checking for the seek player state. Our current decision code up in goal reached is only handling wandering. So at this point we need to add an additional decision to the goal reached event. After we do a check and see that the enemy state is not wander, we'll put an else if statement in place to see if the enemy's state, so enemy.state, is equal to enemy state.seek player. So if we reach the end of a path and find that we are trying to seek the player, then we will invoke navigate to actor, but instead of navigating to a random node, we'll navigate as close to the player as possible. We'll pass in the player reference, so navigate to actor will find the closest path node to the player, and our enemy will begin navigating to the player's location. This should create a scenario where the enemy will continue to follow the player. So every time it reaches the end of its navigation path, it will recalculate a new path to the player itself. So let's jump in and test. And we can see that currently our enemy is in the state of wandering. As long as we stay outside of the sight radius, the enemy continues to wander. But the moment we find ourselves inside of the sight radius, the state changes over to seek player. So right now you can see that the enemy status has changed over. If we go and hide by a path node, you see the moment the enemy reaches the end of its path, it calculates a path to wherever we currently happen to be. So in this way, the enemy will continue chasing us. Now you'll notice something interesting about the way the paths are working. While it is recalculating a new path to our location, it's doing so only after reaching the end of its current path. This means if we set the enemy on a longer navigational path, it doesn't even care that we're following it until it reaches the end of that path and restarts the navigation. So in order to create a believable chase effect, we need to come up with a path regeneration that happens faster than goal end. Now we want to come up with a balance where we do have a faster path regeneration, but not so fast that it happens every single update tick. So as a compromise, what we'll do is we will set up our behavior so that every time it reaches a node when chasing the player, it recalculates the path. So that way many game ticks will go by between path regeneration, but we will regenerate after every path node, so that will give us a more responsive enemy. So as we move around the screen, the enemy will update its path more quickly. Now at the moment, we don't yet have a node reached event. We have a goal reached, and that is the only event that behavior navigation is firing off. So we are going to have to slightly enhance the behavior navigation class. Up here in the navigation folder, we have our behavior nav class itself. If we load that class up, you can see here we have our definition for goal reached. We are going to duplicate this event. We'll declare a second event with the same signature, the same type, only we will call this event node reached. And we will continue to instantiate an anonymous method as a default handler. Now we need to fire off this node reached event every time we reach a new node. So we'll scroll down into our update code, and you can see that we are doing a distance check to see when we hit nodes, and you can see our node index increasing to indicate the fact that we reached a node and moved to the next node. So it's inside of here that we need to fire off the node reached event. What we'll do is we'll do this check after we check for our goal reached. Excuse me. Because if we reach the end of the goal, we would rather fire goal reached instead of node reached. So the last node will not fire off a node reached event. To accomplish this, we will add an else clause to the if statement checking for goal reached. And if we check and find that we have advanced the node but have not reached the end of the path, then we will fire off the node reached event. Again, we need to pass in the event handler signature, so we'll pass in this as the sender object and event args.empty as our arguments. Alright, with this slight adjustment, we now have a new event from behavior nav telling us when we reach individual nodes. Let's turn back to the scene game class now and put this event to work. We'll go and scroll up a little bit as we are setting up the handler for goal reached. We'll actually jump up right above goal reached, and we will set up a handler for enemy nav dot node reached. Plus equals will bring up our new delegate, and or rather tab will bring up the new delegate. Tab again will bring up the method handler, and we can put together the code for what should happen when we reach a node. And again, we can look at this as decision-making code for our enemy. So this is saying that our enemy has just reached a node, and what does it want to do having reached this node? Well, if we're wandering, we're not going to do anything. If we're wandering, our job is to reach the end of that path and do nothing else until we reach the end. So we only want to use node reached if we are seeking the player. Because if we're seeking a player, we want to recalculate the path. Even though we may not be done navigating, we want to set a new and possibly more up-to-date path. So before recalculating this path, we'll do a check and see if our enemy's state is equal to enemy state.seekPlayer. And if so, then we are going to navigate to the player actor. So we will call navigate to actor, passing in the player, and that should take care of updating our navigational path. Alright, with this in place, let's now run the game and test things out. As the game begins, of course, the enemy starts off in his wandering state. Now, if we enter his sight radius, we can see his state change to seek player, but we notice an interesting problem take place. The enemy is staying at this very first node. As a matter of fact, he's getting closer and closer to it and will eventually develop a very tight orbit around it. Now, we can see that his navigation is broken, and he's no longer calculating paths. At first, if you watched really closely, the first few times he crossed that node, he recalculated the new path, because we changed from a short path to this path up in the top right room. At this point, however, he's not calculating any new paths. What has happened, if we jump back out into our code, is we have made a scenario that makes it so that every time we reach the first node, we're of course going to fire off node reached, because we did reach a node and advance. The problem is that node reached is going to tell us to try and recalculate our navigation. That's going to begin with our enemy's position as the closest node, and if he has just reached a node, that means he's sitting right on top of a node. That node is once again going to be picked for the beginning of the path. And the problem with recalculating the path is that resets where we are in the path. So even though we've reached the first node, we're now told that we haven't reached anything and need to reach the first node again. So we do that, we cross the node again, and once again, begin from the beginning node instead of progressing. So what we're going to do is we will adjust the use of the path before we begin navigation. If we think about it, there's no real reason to need to navigate to the closest node, because if we calculate from a closest node, technically that's where the enemy already is. Instead of having to always navigate to the closest node, let's navigate to the next node as the first node in navigation. To do that, we're going to move down to our navigate to actor method. Before we begin navigation, we're going to do a check on our path. And we're going to say if our path has more than one node in it, if path.count is greater than 1, then we will simply chop off the first node from the path itself. This won't hinder our navigation since we had to make a straight line from the first node to the second node anyway. So instead we'll just make a straight line from wherever we currently are to the second node. So we'll take the first the first node of the path and remove it. So that's path.remove at 0. So that will accomplish chopping off the first node. Now, in order to keep our debug visuals updated, we're also going to unmark that node as being part of a path, since again, that visual debug state is actually irrelevant to the actual path that is being used for navigation. So we're also going to grab the path, the first node, so that's path sub 0, and we are going to set its in-path field to false. Of course, we're going to make sure we do this before we perform the remove, since at that point node 0 will be the second node. Alright, with both of these in place, we should now see the adjustment to our paths in place in the game. So let's build and run. And even in the wandering state, if we watch really closely, we can see that every time we hit a goal node and select a new node, the first node in that path is actually one node away. But again, that doesn't hinder our navigation since we had to navigate between these two nodes anyway. Now let's test and see how this affects our seeking navigation. So let's wander into his field of view. He begins chasing us by changing to the seek player state. And now we can see that every time he reaches a node, he recalculates a new path. You can also see that the previous bug is now fixed. Since he always navigates away from the node he was first closest to, this keeps his motion continuous. So now we can see that as he chases us, every time he reaches a node, he recalculates. So at this point, it's very difficult to stay behind him since he's going to keep turning around to chase us at our new location. Now there's a small amount of lag, of course, as he has to navigate to a node before he recalculates, but that's simply a compromise between the responsiveness of the enemy and the amount of processing power that is put toward recalculating the paths. Since again, we're doing our path recalculation efficiently, since he only recalculates every time he hits a node. So with this now, we have the ability for our enemy to seek the player and to chase him all around the level using the path node network. So with that, it's now time to move on, and that will bring this video to a close.